low volume of my voice, but at the end, COVID managed to catch me, so I'm trying to fight back. Anyway, in this talk, I will present some work that we are doing at Milano Bicocca concerning the massive black hole evolution, and specifically focusing on the evolution in clumpy galaxies. This work has been done by myself in collaboration also with Elisa, Alessandro, and Massimo. So, massive black hole. We know that they are observed at the center of several galaxies where they are a source for powerful activity, both electromagnetic and dynamical. On the large scale structure level, we also know that galaxies that form in a hierarchical ways can undergo merger event during their life. So we can think about the formation of binaries of massive black hole as soon as two galaxies hosting one massive black hole merge. And so this binary can form, evolve within a single galaxy, and they can emit gravitational waves that can be observed, hopefully, by LISA. However, things are not so simple because, as you may know, two black holes inside realistic galaxies are really tiny objects, and they have to cover something like 10 order of magnitude in separation to reach the final coalescence, as depicted in this sketch here on the right that you already seen this morning. So in order to investigate properly the processes that drive this evolution, we need to investigate the quite rich phenomenology that massive black hole experience at all scales. And here we have to face the long-standing dilemma of astrophysics. So we can use a fully numerical method that are generally much more accurate in describing the true physics behind a process driving the evolution, but they are generally expensive. So we cannot run an extensive parameter space exploration. On the other hand, we have semi-analytical methods that are much more idealized setup. They rely on several approximations, but they are generally much faster. So we can systematically explore parameter space. There are several levels of semi-analytical modelization in which the approximation can be larger or smaller. And the best semi-analytical methods are those that are validated against fully numerical methods in order to have under control these approximations. And in this talk, I will focus on semi-analytical methods. And we will use these methods in order to study the large scale evolution of massive black holes, so before the actual formation of a binary. In order to do so, we need a list of ingredients that have to be considered. So the fact that galaxies are not very simple objects, but they are generally multi-component. We need reliable description of the dynamical friction, so a process that extracts energy and angular momentum from the orbit of the inspiring massive black hole. We also need to model tidal stripping of the infalling satellites, because generally massive black holes are not naked, but they are surrounded by stars that can be stripped by the tidal field of the galaxy. And lowering the mass, the effective mass around the massive black hole lowers the effect of dynamical friction. Other things are, for example, the evolution of the galaxy structure itself that can influence the dynamics of massive black hole. And finally, galaxy clumpiness, that is the topic of this talk. So here at Milano Bicocca, we are trying to construct a general framework in order to take into account all these kind of phenomena in a single semi-analytical model in order to describe at best the evolution of massive black hole. But here I'm focusing on the clumpiness. So dynamical friction, as you know, is generally considered the main process driving massive black hole evolution on a large scale. But when we consider the actual shape and structure of realistic galaxies, this cannot be always the case. For example, if you have a prominent bar within a galaxy, then dynamical friction is counteracted by the stochasticity that can arise because of the interaction between the massive black hole and the bar, for example, as was investigated in this paper here. Other sources of stochasticity are clumps. In fact, when we have massive galaxies with turbulent gaseous disks, they can develop clumpy interstellar medium, and these clumps can be very massive, up to several million solar masses, and a massive black hole can have stochastic interaction with them. And one might expect that massive black hole could undergo a rapid sinking or erratic dynamics. However, as I was saying, galaxies are complicated objects, so we need to provide a meaningful description of them. So we need to find something between the good old spherical cow and what we actually observed in our universe. So we need a balance between the need of realism and computational efficiency. To do so, we are building this semi-analytical framework in which we model galaxies through the superposition of smooth fixed potential that can be of any shape, spherically, axisymmetric, or even triaxial. Then we can model the dynamical friction also in rotational supportive structure, for example, a disk-like galaxies, a work that has been validated in this work here against full embodied simulation. And to mimic clamps, we are introducing particles that are not point-like. For example, particles that can follow a density profile, for example, the Plummer one. So particles here are treated as a set particle in the galactic potential, and the trajectory is generally obtained by a cheap numerical integration. But the point-like particle, so massive black hole, and the extended particle, clamps, can additionally feel their self-gravity, so they can interact among themselves. So this is not new because it was already investigated in the past. For example, here in the work of Roskar in 2015, they analyzed a fully hydrodynamical cosmological, well, maybe not cosmological, but fully hydrodynamical simulation in which the two galaxies can develop a clamp interstellar medium. And they analyzed the evolution of the pairing of the binary in this kind of simulation. And in fact, they found that the interaction with clamps can delay the in-spiral of the massive black hole toward the galactic center. And in fact, the black hole can exit the galactic plane. So here was only a single simulation because hydrodynamical simulations are really expensive to run. And if we have a semi-analytical model in which we can simulate this kind of process and extensively analyze the parameter space, could be much better. And that's what we have tried to do. So we consider a galactic system to mimic a Milky Way-like galaxy. So we consider a galaxy formed by three components: a dark matter halo, an exponential disk, and a stellar bulge with these masses here. Then we consider clamps that are sampled from the exponential disk profile with a velocity chosen close to a fraction of the local circular velocity, and with masses sampled from a power law of this shape here. And the extreme of the power law are given in the next table in a minute. The massive black hole are placed in the disk plane of the galaxy, and they are given the initial velocity is given a fraction of the local circular velocity, with masses drawn from a log-fed distribution between 4.5 and 7. So these are the initial conditions, and we consider two broadly, let's say, two groups of simulations. So a low redshift Milky Way galaxy with this scale radius of the three components, and a high redshift version in which the scale radius are reduced. So we have a much more compact galaxy with the same mass, of course. In this kind of high redshift galaxy, we also consider much more massive clamps. In fact, the mass is sampled between 10 to the 7 and 10 to the 8 solar masses. And we consider also fewer clamps in this high redshift galaxy with respect to the number of clamps in the low redshift Milky Way example here. And for each case, we run 20,000 simulations. And for each simulation featuring clamps, we run a twin clamp-free simulation to find the spiral time in a smooth galaxy, so without clamps. And here what we have found. So in this corner plot here, you can see the correlation between the parameter that we are essentially varying. And the color code is given by this quantity here that you can also see here. So it's the time difference between the spiral in the galaxy with clamp minus the spiral in the galaxy without clamps, normalized to the spiral time in the galaxy without clamps. And so here in each pixel, you can see the average value of this object here. As you can see, for the low redshift Milky Way, there is no strong effect on the spiral, since the color scale is essentially quite uniform. And also from the histogram here, you can see that the distribution is almost symmetric around 0, with very small time difference between the two sets of simulations. The situation changes when you consider the higher redshift Milky Way, in which we have much more massive clamps. And in fact, you can see that in some region of the parameter space, there is a clear delay of the spiral of the massive black hole. For example, here for low mass massive black hole, and when we have a large number of clumps. Here, for example, we are going towards 10. And from the histogram, here you can also see that the distribution is highly skewed towards positive delay. So this means that if a galaxy hosts clumps, then the interaction tries to delay the spiral of the massive black hole rather than promoting it. So this is also visible here, the difference between the low redshift and high redshift Milky Way. So here the situation is quite boring because here we have the ratio of the spiral time with clumps and without clumps as a function of the black hole mass, and the ratio is around 1. So nothing really interesting here. The situation is different for the high redshift case, in which you can see that depending on the mass, there is a clear trend towards more positive delays for lower mass black hole. And in fact, here that's because dynamical friction is essentially much less efficient for low mass black hole, and so they are generally perturbed by interaction with clumps in a much more easier way. And finally, we can also see that in the high redshift galaxies, a lot of black hole cannot reach the central region of the galaxy, but they stay outside. In fact, here you can see the final radius reached in the simulation when you have clamps and when you don't have clamps. So when you don't have clamps, all black holes reach the center, essentially, while when we have clamps, a fraction of black holes remain outside the galaxy. So in principle, this could be a problem for low redshift, for low mass massive black holes that are generally those that could be observed by LISA. And I can directly jump to my conclusion. So in our preliminary set of semi-analytical simulation, we found that clamps can influence the dynamical friction in spiral only if their mass is sufficiently high, above 10 to the 7 solar masses. When there is a noticeable effect, clamps generally delay the spiral, and the effect is stronger for small mass massive black hole. For example, those that can be hosted by high redshift galaxies could be this the target for LISA. And then we envisage a few improvements for our study. For example, we can consider more physically motivated mass and size for clamps, for example, based on the Thurs disk for the Thurs profile of the disk. Also consider a different clamp lifetime that here was considered to be essentially infinite. But we know that clamps can dissolve, and then we can consider different nature for the clamps that can be molecular clouds or even star cluster, and they have different lifetime. And then this study, as I was saying, is intended to be framed into a more general semi-analytical framework describing how massive black hole evolution in realistic galaxies can be modeled. Thanks a lot.
Thank you, Michael, for the talk. Maybe we have time for one question.
Matteo, so very nice talk. It's Lucio asking the question. So when you say that you have a fraction of the black hole that is ejected, it doesn't make to the center, you also allow for the possibility that some dynamical friction will happen outside the disk of the galaxy, because they will end up in a spheroid outside the disk, but there will still be some matter.
Yeah. So yeah, dynamical friction is provided by all components. So for the disk, the bulge, and also the dark matter halo. But of course, outside the disk plane, the density is much lower, and so the dynamical friction is less efficient. And so these black holes cannot reach the center. Yeah.
Thanks.
Okay, thank you again. If anyone has other questions, please submit them on the website. We should move on now. The next talk is from Andrea Derkutsky. He's going to talk about extreme mass ratio in spirals in ACM fusion disk.
Okay, I'm Andrea. I'm a postdoc at the University of Zurich, and I'm going to talk about a formation channel for extreme mass ratio in spirals. So this is when you have a central supermassive black hole and some stellar mass type black hole that's in spiraling in the LISA bands. Okay, just to start with the basic points, we know black holes have to accrete to grow to the masses we see today, right? So we observe AGN of all different types and at different redshifts. And while there's some uncertainty in the duty cycle of AGN, we expect that galaxies spend at least a few % of their lifetime in active phases. Here's just one example of what that might look like, but there's a huge variety. And so if we expect MREs to form in all galactic nuclei, then we should expect at least a few % of them to form in these types of environments, assuming that the presence of gas does not affect the MRE rate. Okay, and this is also neglecting nuances depending on black hole mass, redshift, etc. Okay, so we can't spatially electromagnetically resolve accretion flows like this, but we have lots of models that give us an idea of what this flow should look like. So typically we expect the gas disks at small scales to be geometrically thin and rateably efficient. And this implies it can be relatively dense compared to other types of accretion flows. Okay, so let's look at a cartoon, not to scale, of an AGN disk. This type of disk has a lot of implications for different types of gravitational wave sources at a range of frequencies. So, for example, galactic nuclei are a pretty crowded environment. So if you have stars or black holes that intersect the disk, through each intersection, there's an exchange of energy and momentum. It can change the inclination. So with enough intersections, the stars or black holes can be embedded. You can also, in regions where the gas disk becomes gravitationally unstable, you can form stars in situ. So that's what I'm focusing on in this talk. And so once stars or black holes are embedded in the disk, they can then migrate or move to different separations. They can accrete and grow. They can maybe merge with other black holes. So that's an interesting LIGO channel. And at some point, they might find themselves in the center of the disk coalescing with a central supermassive black hole. And in the right mass range, that's a very unique Lisa source. So there's some recent work actually that calculates how the conventional dynamical MRE formation scenario can be affected by the presence of a gas disk. Typically, they find that it boosts the MRE rate. So this is because the presence of gas basically enhances the amount of black holes that you can get close to the central supermassive black hole. So I'm going to be talking about some recent work that I did with Lucia Meyer that's about this in situ channel here and how that can also produce MREs at potentially a comparable rate, but the rates are highly uncertain, and I'll get to that. Okay, so there's a lot of complicated processes involved getting, from gravitational instability down to an MRE, and I can't focus on all of them here, but let's just go over a few of the basic points. It's been known for a long time that gravitational instability in massive disks will lead to the formation of spiral density waves. And if the gas can cool efficiently enough in these regions, then these density enhancements will lead to fragmentation. So you get the collapse of these bound coherent structures. A lot of this work is done in the context of forming another formation pathway for planets and protoplanetary disks, for example. In the AGN case, you're going to form stars. So with perturbation theory, you can derive the mass or size scale of clumps that form. However, there is a lot of work that shows that when you actually run simulations of fragmenting disks, the resulting clumps will differ from analytical predictions. That's for a range of reasons. So for example, clumps can have lots of rotation. They can be born on eccentric orbits. If you include things like magnetic fields, you primarily find also a different size distribution of clumps. So there's a lot of reason to expect that clumps might actually form on smaller scales, for example, or there could be some deviations from the theory. So we don't know necessarily what the outcome of fragmentation is in all cases, but the simulations can help us calibrate what we expect, okay? So let's look at a few of the important scales in this problem. Gravitational instability usually sets in at the outer radius, so that's when the self-gravity of the disk is overcoming the rotational and pressure support. And if the gas can cool enough, you're going to form stars at maybe 0.01 parsecs to a parsec, depending on the gas disk. Okay, once stars form, they can migrate. This is through an exchange of angular momentum with perturbations in the disk. So they can find themselves at smaller separations. If they get down to around tens of Schwarzschild radii or hundreds, they might encounter something called a migration trap. That's where the direction of migration suddenly changes sign due to nuances in the disk structure. This is faded out because I'm not actually going to talk about it, but I wanted to point out that it can happen. If you reach smaller separations, stars can be subject to tidal forces from the central supermassive black hole. This means that they would be destroyed in some way, depends on their orbit and things like that. It also depends on the mass of the central supermassive black hole and details about stellar structure. But typically you expect it to occur within roughly tens or so terrestrial radii, depending on parameters. If stars can survive this phase, so for example, maybe they collapse to black holes before they reach that point, then they will find themselves in the gravitational wave dominated regime and be an interesting LISA source. So if you want to calculate an Emery rate, you can think about breaking this into some steps. So first you need a solution for your disk structure. And with that, you can then determine where does fragmentation happen, and based on the properties there, what types of clumps or stars do you expect to form. So with this, we're going to make some assumptions, like things like a steady state, constant accretion rate. The gas can be supported by radiation and gas pressure. You could solve for the vertical structure with a set of opacity laws, etc. Okay, so then you can derive an initial distribution of stars. And then you can calculate the migration of stars in said disk model. Then you can look at, how many stars should become disrupted, how many stars may collapse at different times while they're migrating through the disk. Maybe you can consider accretion of the stars. And in the end, you can count how many Emrys you get from one fragmentation episode, okay? So after the, over some time scale, this gives you an Emery rate. So there's obviously a lot of uncertainties in each of these steps here, and I can't really go into all the details. Despite how intimidating all these uncertainties might be, I'm going to try and show you some Emery rates. Okay. So some of the basic takeaways for this picture, star formation in AGN disks is expected to form typically more massive stars than star formation in the ISM, just because you have stars forming in denser and hotter environments. So this is the case. We can find this, we can derive this from the disk models. However, the range of masses formed in each disk is not the same. So here I'm showing a histogram of a mass distribution of stars that form as this is a stellar masses and the number, and the different colors are different black hole masses or different prescriptions for viscosity in the disk. So the point is that this range varies a lot, right? Actually, this is the initial stellar mass distribution, and for some cases it can start really small because you form quite small clumps initially. So let's focus on just one mass distribution to simplify the picture. This is for a disk around 1 million solar mass black hole, so it's interesting for LISA. You start with initially subsolar mass stars, the peak of your distribution, but this is not fixed in time. If there's still gas around, the stars will of course accrete and grow, so the distribution will evolve in time. So here's an example of how that can happen. According to a semi-bondy type accretion prescription, I say it's limited a bondy prescription because it's based on accretion rate to a bondy radius, but that size is actually limited by the thickness of your disk. So it can actually, at some point, the accretion rate is reduced based on this mass of the star. So this is an example of how your mass distribution might evolve over the time scale it would take stars to migrate into the inner regions of the disk where different outcomes might happen. So calculating, the migration rates of stars, you can then sum up how many are disrupted or how many become black holes and are seed potential Emrys. So here I'm shading the mass distributions with the ones that become extreme mass ratio in spirals. So here, this dashed line case is assuming the stars didn't accrete at all. It's not very realistic. We expect there to be some growth. And of course, the other case, all the stars were accreted and they eventually can survive and seed potential Emrys. So of course, understanding the accretion rate and growth of stars in disks as they migrate is a really important thing that has implications for the resulting Emery rate. Now, if I sum up the number of Emrys and divide it by the disk lifetime, I can have a rate that's a function, or a rate per AGN activity cycle. So that's what I did for a whole set of disk models. So varying things like the black hole mass, the accretion rate in the disk, whether or not you have stellar accretion, different migration models. So you can have a lot of different outcomes here. The main takeaway is that, first of all, let's focus first on this this left side here. This is where a 10 to the 6 or mass black hole. This is where tidal disruption is the main inhibitor of emery formation because stars need to survive this phase to become emeries. In that case, emeries are not guaranteed because you need to have enough accretion. But for realistic or reasonable estimates, you can form emeries, and if you do form them, they happen at a range of 10 to the minus 7 to 10 to the minus 5 per year per AGN. If you have a slightly larger supermassive black hole, TDEs are less of a problem because of where the tidal radius is compared to the ISCO. So you can form more emeries, and even across a range of migration accretion models, the rates are, an order of magnitude different, but still quite high. Okay, this rate is maybe a random number to you, so let's compare it to rates from other papers. For example, there are estimates of emery rates based on just dynamical formation channels, for example, two-body relaxation in dry nuclei. And for those rates, you might predict something like 10 to the minus 6 to 10 to the minus 5 per year per nuclei. So this is actually in the ballpark and really similar. Unfortunately, the rates for the in situ channel are really uncertain, right? So they may be much less, they might just be a subset, but they could also potentially be comparable to or greater than the emery rate in dry nuclei. That's the main point that I want everyone to take home with them. So if I were to convert this crudely to a volumetric rate, I can look at the average accretion rate onto black holes in the relatively local universe, meaning up to redshift 1. And that implies a volumetric rate of less than 1 to 10 per year per gigaparsec cubed. This, of course, should really take into account nuances with, how many AGN you have at a certain mass range and accretion rate in the local universe. So this can be improved. But the takeaway is that these systems could be more common than previously anticipated, simply because AGNs can boost the emery rate. So in the last minute, I just want to take a point to mention a completely different topic that deserves its own talk, but I just want to give a shout out to why these sources can be really interesting in LISA. They are born in gaseous environments, but they also are still in gas when they reach the LISA band. So this means that gas can influence their in-spiral while they're emitting gravitational waves. This is a nice illustration by Laura Sperna from a meeting last week on probing black hole environments through gravitational waves. So there's a lot of work being done on this. I'm very happy about that. The interesting thing about this, maybe it's also intimidating, is that, the main effect from gas is to exert a torque during the in-spiral. And it's really thought now that that's the most dominant type of environmental effect compared to other exotic things. However, the torque exerted by the gas is not super easy to predict. So here's an example of simulations of gas torque on an emery during the in-spiral in the LISA band. And if you change some of the gas parameters, you get outward or inward torques, or you get really variable torques. This is another reason to want to do a simulation comparison in this regime, right? Because we would like to know what types of signatures happen here. The positive spin is that if we could detect it in the waveform, you could actually have a measure of the environment. So you could probe these small scale things that are electromagnetically not resolvable. So I'll just end there with some conclusions. The main point being that you can form emeries in situ in massive AGN disks. The rates, the masses, or the orbital characteristics depend on a lot of things like stellar accretion, evolution, etc. So there's a lot of follow-up work to be done here. Binary interaction is also a very important thing we'd like to consider. And these sources can be really interesting for LISA. So I think I'll end there.
Thank you, Andrea, for a great talk. Maybe we have time for one question.
So I have many actually, but I will speak to one. So what is your expected distribution of eccentricities for those emeries?
Good question. We don't consider any eccentricity. Oh, you mean when they enter the LISA band?
Well, more like in general throughout the evolution, because if it's very high, you can expect two-body relaxation to deflect your in-spiral, and you have to consider that, I guess.
Yeah. I think it's a really important point because, first of all, we know that when stars are born via fragmentation, they are born on eccentric orbits. In this work, I don't consider that. So I just consider migration assuming circular orbits, and eccentricity will affect the migration and the interaction, as you're saying. I do think some of this eccentricity could be still present when they enter the Lisa band, but I don't have a number for you. Yeah, I expect it to be much smaller than the dynamical scenario, of course. But that's something we'd like to look at with full simulations. So, yeah. Right.
Nate, is your question short? So maybe you can quickly ask. Otherwise, write it down.
Yeah. Oh, sorry. Did you call me?
Your hand is up. I thought you have a question.
Yeah. Thank you. I'll be real quick. Hi, Andrea. I wish I could be there in person to see you again. Great talk. I was wondering, in terms of these stars migrating and forming black holes, right? Assuming that they undergo core collapse, can they get kicked out of the accretion disk? Is that possible? I assume it's possible. Is that something that you take into account?
Good question. So I don't explicitly take it into account. I just say over some stellar lifetime, it eventually becomes a black hole, but it's definitely there could be some recoil. I can say at what part or what separation in the disk that happens. And by the time stars collapse, you expect that they have migrated towards the central black hole quite substantially. And so it happens pretty deep within the potential. And I don't expect them to get, ejected from the system entirely. But there could definitely be some change in the, their inclination. So that should be considered in the future.
Thank you.
Okay, thank you again. Sorry, but we have to move on. Again, please feel free to post your questions in the website. Our next talk is from Chris. And
yeah, hello. Can you guys hear me? I'll share my screen here.
We can hear you well.
Okay, great. So hello, everyone. My name is Chris Teedy, and I've just finished up my graduate studies at NYU. And one of the main things that I work on was the orbital evolution of binaries embedded in gas. So today I'll talk about some work I did thinking specifically about massive binaries and potential Lisa sources embedded in circumbinary accretion disks. So generally, what are we thinking about when we're thinking about these massive binaries embedded in accretion disks? We're thinking about, you form a massive or a supermassive binary following some galaxy merger, and this binary is able to shrink its orbit somehow down to about parsec or sub-parsec scales, but still wide enough separated that gravitational waves are not efficient enough to merge the binary within a Hubble time. And then for the gas, we imagine some gas coming from large radius with some angular momentum coming in a coplanar way. And we imagine that it's both optically thick and radiatively efficient so that it radiates away its vertical pressure support and collapses into a geometrically thin, rotationally supported accretion disk. And then we care about the presence of this gas, because following these galaxy mergers, you can drive lots of gas to the new galactic nucleus. So we expect this gas to be there in many cases. B, this gas can influence the orbital evolution of the binary. So it can change the binary semi-major axis and the binary eccentricity. And then the gas also offers a possible observational channel by which to identify these compact massive binaries in electromagnetic surveys. So when people actually simulate this problem in order to study it, typically when you're thinking about the orbital evolution, because of the long simulation times required to get a converged and relaxed result, people do this in 2 dimensions, typically, and they tend to do so either for or in reference to kind of a classic or fiducial model. So in this kind of fiducial or classic case, the binary is usually taken to be equal mass and fixed on a circular orbit. The disk is taken as kind of a classic Shakura-Senyaev alpha disk, where we assume that there's some subgrid underlying turbulence that gives us some effective kinematic viscosity in the disk that we parameterize through this dimensionless value alpha. And in this kind of historical model, alpha is taken to be 0.1. The disk is also usually assumed to be isothermal, where sigma here is the vertically integrated surface density of the disk and P is the vertically integrated pressure. And then to round this out, we have to assume some characteristic scale height of the disk. So the thickness of the disk H at every radius R. And in this kind of fiducial case, this is taken to be 0.1. And then here I've also written that if you impose vertical hydrostatic equilibrium in the disk, you get that the scale height is inversely proportional to the Mach number of the flow. So as you go to thinner and thinner disks, you get a more highly supersonic and a colder accretion flow in your circumbinary disk. So when you do this, you get the kind of characteristic structures for this problem. So you get this deep depleted cavity. It's lopsided and precessing. You form these stream structures that connect the binary, or that move gas from the cavity wall onto the binary itself. And then each of the binary components develops its own circumsingle disk that we typically refer to as a mini disk. And then kind of the classical picture of circumbinary accretion, people thought that the disk and the gas disk would absorb angular momentum for the binary, pushing it closer together, shrinking its orbit, and helping to shepherd it on its way to a gravitational wave dominated regime and potentially to merger. But in the last 3 to 5 years or so, a number of groups using high resolution hydrodynamic simulations have actually found that the opposite happens for this model. The gas delivers angular momentum to the binary, and so much so that it's actually driving the binary apart. So this is a classic plot where the red line shows the angular momentum current through the disk, and that this angular momentum current onto the binary is positive, and so much so that it's causing the binary to grow its semi-major axis. So if we're thinking about these massive compact binaries and galactic nuclei, the presence of a gas-driven phase could actually serve to inhibit and potentially delay the binary from getting to a gravitational wave dominated regime and potentially to merger. But one of the kind of big caveats to this fiducial model, among many that you could point out, but is that if we're thinking about these compact massive binaries embedded in AGN-like accretion disks, this value of H over R of 0.1 is about an order of magnitude or too hot and thick for what we would expect. So this number is appropriate for things like protostellar disks or protoplanetary disks. But for AGN-like accretion disks with a compact binary in them, we would expect this to be more like 10 to the minus 2 or 10 to the minus 3. So Mach numbers of like 100 or 1,000. So in order to see how this changed the orbital evolution of the binary, I did some work where we systematically raised the Mach number in our study. So we're considering thinner and thinner, colder disks, where here Mach 10 is the kind of fiducial case, the warmer and thicker case, and Mach 40 is the thinner, colder case, or the thinnest, coldest case that we look at. And we find that you get the same general morphology, but that there are some different characteristics as you change this flow. And when we measure the change in the binary migration rate, what we find is that for these comparatively warm and thick disks at Mach 10, we do find out spiral, that the gas is delivering angular momentum to the binary and driving it apart. But as you go to higher and higher Mach numbers, so thinner and thinner disks, we find this monotonic decrease in the binary migration rate, such that it crosses 0 at a critical Mach number, in our case, of about Mach 25, such that disks with H over R less than about 0.04, the gas actually switches to removing angular momentum from the binary, shepherding it closer together, and then potentially into a gravitational wave dominated regime. So in order to understand why this is happening, we can break this binary migration rate into 2 main components. The first is that due explicitly to the physical accretion of gas and angular momentum. That's this dashed dotted line that doesn't change very much. And then the other is that due to the gravitational torques from the gas on the binary. And that's this dashed line. So what we find is that there's some morphological change to the distribution of gas in the disk that's changing our gravitational torques and giving us this transition from binary out spiral for comparatively warm and thick disks to binary in spiral for colder, thinner disks, more closely representative of what we would expect for like a typical AGN disk. So in order to understand this better, we broke our disk into 3 separate regions. An innermost region, which is the red curve here, which includes the binary itself and the mini disks. A cavity region, which is the blue curve here, which includes the cavity wall and the streams, and then the outer circumbinary disk, which is shown in yellow. And we see that as we go to thinner, higher Mach number disks, the torques from the innermost region and from the outer circumbinary disk don't change very dramatically. But what's really changing is that we're getting growing negative torques from this cavity region. So something about the cavity wall and the stream structures is changing and giving us stronger and stronger negative torques and causing this sign flip in our binary migration rate. Excuse me. So in order to understand, or we can understand why this is, if we look at time averaged maps of the circumbinary disk surface density and torque density. And what we find is that this, in a time average sense, the cavity has this kind of characteristic egg-like structure. And we see why it gives us negative torques, because the far sides of this egg extend into quadrants of positive torque. So quadrants trying to speed the binary up, give it angular momentum and spread it apart. And the near sides of this egg extend into quadrants of negative torque. So they're trying to pull back on the binary and slow it down. So that when you integrate around this kind of cavity structure, you get a net negative torque. But as you go to thinner and thinner disks or higher and higher Mach numbers, we find that this time average cavity structure stays almost identical. And the main change is that in order for the circumbinary disk to maintain its kind of quasi-steady configuration against this internal egg beater from the binary, it packs more and more mass into this cavity wall and cavity structure, and leads to more and more negative torques, such that they eventually become the dominant contributor to the total torque and cause this sign flip around Mach 25, so that for thinner disks, we get binary in spiral. And then it's worth mentioning that since doing this work, a number of other groups have looked at this effect of changing the disk thickness on the binary orbital evolution. And they all find in some capacity that comparatively warm and thick disks lead to binary out spiral, but thinner and colder disks lead to binary in spiral. And then where your critical Mach number is, where you actually change your sign, can vary a little bit as you change things like the mass ratio of the binary or the value of the viscosity in the disk. Okay, so we've talked about how changing the thickness of this. Oh, okay. Sounds good. I'll go quick through the last part. So we've talked about how changing the thickness of the disk can change the sign of your migration. But another place where you can relax this kind of fiducial model is you can consider an eccentric binaries. You can no longer require it to be on a circular orbit. So in work led by Jonathan Zrake, we looked at eccentric binaries, and here we're showing E dot. So the change in E is a function of eccentricity. And the important feature here is that we find two equilibrium points. So first we find that circular binaries or near circular binaries tend to stay circular, but that any binary that's born with an eccentricity of greater than about 0.1 is driven to this other equilibrium value at about 0.45. And if we look at the change in binary semi-major axis, we see that for these comparatively warm and thick Mach 10 disks at circular, they're driven apart. But at the other equilibrium eccentricity of about 0.45, the gas is actually causing the binary to shrink its semi-major axis. And then lastly, this equilibrium eccentricity is observationally potentially interesting, because if you have a binary that's driven into a gravitational wave dominated regime by a circumbinary disk at this equilibrium eccentricity, it's enough eccentricity for it to retain a detectable level of eccentricity upon entering the Lisa band. So measurements of such small eccentricities could potentially be used to say something about the frequency and relative importance of a gas-driven phase in the total lifetime of a massive binary on its way to merger. So maybe I'll just put my conclusions there and end and take a question or two if anyone has them.
Thank you for a great talk. Maybe we have time for.
So very nice talk, Chris. Maybe you said it and I just didn't notice, but what equation of state are you using? Is the models or isothermal or adiabatic? Or we have fully
we're using an isothermal equation of state.
isothermal. So the reason why I'm asking is because I wonder if you were using adiabatic or adiabatic with some cooling, then you have this other effect that the shocks at the rim of the cavity and also the shocks near the needles will change as you change the thickness of the disk. So that might change the torques.
Yeah, so if I'm understanding you correctly, yeah, it's certainly true that the shock heating at the inner edge of the cavity could puff up your disk. So that's something that we're actually thinking about and working on now. But if we're thinking about these really realistically thin, like Mach 100 or Mach 1000 disks, it's not clear to us if you could really puff it up to a point where you're in this out spiral regime or not. But that's something that we're thinking about now. Yeah.
Yeah, thanks.
Okay, if there are no other questions, then let's thank Chris again.
Thank you.
And let's move to the next talk from Luke Kelly. This is about supermassive black hole binary populations. Are you here, Luke?
Yes. Can you hear me?
Yes.
Great. Let me just try to share my screen here. Okay. You can see that okay?
Yep.
Great. All right. Yeah. So it's a pleasure to be joining in. I'm sorry it's not in person, but this will have to do. So good morning, everybody. I'm going to talk a little bit less about science in this talk and really more about kind of tools and frameworks. But I'm still really excited to present kind of this new effort to you. And this is really a nanograv effort that we've been leading, especially in the astrophysics working group. So as the title suggests, this is a kind of a new software framework called Holodeck. And this is population synthesis, just like you would have for kind of stellar mass binaries, except this is really for massive and supermassive black holes. That's what I want to tell you about. So the kind of immediate motivation for this is that in nanograv, which is a pulsar timing array, we're seeing a signal that seems to be consistent with gravitational waves, low frequency gravitational waves, in particular gravitational wave background. But really that's the topic for another talk. But in general, we're really expecting to be very soon moving from doing inference on upper limits to doing inference on actual detections. So that's kind of necessitating a much more kind of systematic and robust framework. And specifically previously in our data papers, the collaboration would choose a specific type of model, typically a semi-analytic model to generate massive black hole binary populations, and then use the upper limits from gravitational wave measurements to do kind of basic analysis on that. We wanted to move to a much more kind of unified and inclusive approach where instead of choosing somebody's favorite model, we're really able to use a variety of different models from any member of not only the collaboration, but also the broader community. So this is trying to really be much more unified. In addition, the core of it is we really want to be extremely robust. And what that means to me is that we're willing to sacrifice perhaps how tight the constraints that we're making are to really make sure that they're accurate constraints. And we're not going to come back 5 years later and find that, oh, actually the most likely parameter space is outside of our previous contours or something. And I think in practice, what that means is trying to take into account the systematics in addition to kind of the statistical and parametric uncertainties. Of course, it's also great to be reproducible, to have kind of good software practices, and we really want this to become a kind of open source tool that's very broadly usable by the community, not just other pulsar timing arrays like the European pulsar timing array, but general astrophysics investigations and also LISA in the future. So we've definitely been considering expansion to modeling LISA sources in the future, and that's really shaped the way that we've structured this code framework to make it very easy to just plug in different types of simulations. If you're focusing on higher redshifts, lower masses, MREs or IMREs, that should be very possible to do. Also, kind of down the road, we really want to be able to use this framework for doing kind of simultaneous constraints, not just using gravitational wave measurements, but also taking into account electromagnetic observations. So both binary candidates, for example, the periodic variable AGN that have been identified, but also just single AGN properties. Those are still constraints on massive black holes. So things like the AGN luminosity function, galaxy scaling relations, things like that. So this really translates into kind of two key requirements that we need. One is just to be able to very rapidly map, to be able to do inference, rapidly map between astrophysical parameters and then gravitational wave signals. So populations of binaries and then the gravitational waves and electromagnetic counterparts that they produce. At the same time, we want to really be systematically characterizing and including all of the relevant uncertainties, both systematics and statistical, as I already mentioned. So kind of the way to handle these two requirements, first in terms of rapid mapping, is we kind of have a multi-staged approach where perhaps you start from cosmological simulations or you use semi-analytic models, and then separately you do massive black hole binary evolution. You construct gravitational wave libraries, large catalogs of sources and gravitational wave signals, and then in a separate stage, we're approaching this using some sort of emulation. So we've been working on Gaussian process emulation, but it's also easy to imagine something a little bit fancier like neural networks or something like that to really speed up this process on the inference stage. In terms of taking care of systematics, the approach that we've taken is to essentially be marginalizing over hypermodels. So not only the individual parameters like scaling relations or hardening processes, but be able to use either cosmological hydrodynamic simulations or semi-analytic models or observational-based catalogs and be able to do that all at the same time. And just to kind of drive home the importance of taking into account these systematics, I really like thinking about the galaxy-galaxy merger rates. So I'm showing here on the left, these are the galaxy-galaxy merger rates based on dark matter-only cosmological simulations, the Millennium simulation, and then populated using semi-analytic models. And on the right is using cosmological hydrodynamic simulations. So on the left, you'll see that the galaxy merger rates have almost no redshift dependence and very strong mass dependence. So almost 1.5 orders of magnitude difference in as you change the stellar masses. Now on the right, from cosmological hydrodynamic simulations, you see the absolute opposite thing. So there's very strong redshift dependence, 2 orders of magnitude variation here, and almost no variation in the stellar masses. So these types of results, even if you're tuning the parameters of your models, of your simulations of either type, you're not going to fully encapsulate the differences between these different parameter spaces. And ultimately, it doesn't really matter which one of these happens to be right. We just want to make sure that we're encapsulating that so that eventually the data can inform the accuracy of the models. So the structure of the framework that we've ended up, I'm trying to depict here. So when you're doing massive black hole binary population synthesis, we've kind of broken this up into 3 key stages. So first, you need some sort of merger rates, typically galaxy-galaxy merger rates, but in some cases you can skip ahead to black hole. You need to be able to populate with black hole properties, masses, mass ratios, perhaps eccentricities, redshift distributions, maybe accretion rates. Then you need to do the actual binary evolution, and this includes some combination of dynamical friction, stellar scattering, interactions with a circumbinary disk, just like what Chris was talking about a minute ago, and gravitational wave emission. Then we generate our simulated gravitational wave signals, create a library, and then do emulation and inference comparing to actual gravitational wave measurements. And that lets us feed into constraints posteriors on the astrophysical parameters that are going into this. So the approach to handle the systematics is really to make this extremely modular so that each of these different components, you can plug in your favorite type of model for each one. So for example, for the galaxy merger rates, you can use Millennium simulations plus abundance matching, you can use observational catalogs, or you can just use directly cosmological hydrodynamic simulations. And similarly, you can use the same type of approach for all of the other components. And by mixing and matching the different combinations of these, you're really fully marginalizing over not only the parametric uncertainties, but the systematics also. So in practice, this is all in mostly Python framework. There are some C and Numba extensions to speed things up. I don't think I need to go into the details of the code structure here, but we've really tried to make this extremely user-friendly in addition to powerful, performative, and extensible. So here I'm showing an example of within a Jupyter notebook, how you would set up one of the semi-analytic models. And the way that semi-analytic models typically work is you kind of need 3 key components. You need a galaxy stellar mass function, pair fraction of galaxies, and then a galaxy merger timescale. And also kind of to translate between different parameters, you need some sort of black hole galaxy host relation. So in this case, we're using a bulge relationship. So you just create objects for each of these, plug them into a semi-analytic model, and then you can immediately just call out for parameters, resulting parameters. So here, for example, I'm showing gravitational wave, the distribution of gravitational wave background amplitudes at a particular frequency. And here is also showing a full spectrum. So this framework is already kind of working in its most basic sense. There's still a lot of kind of testing and smoothing out and performance improvements that we're working on, but we're very excited that this is coming together and already really becoming useful. So the team that's actively working on this is really pretty extensive, actually coming from around the world, not just the US. And of course, we're very excited about having additional people come in and collaborate on this. So there are a lot of different components that we're working on, from kind of realistic sky maps and detection analyses to kind of most up-to-date state-of-the-art galaxy black hole scaling relations, and including realistic accretion and circumbinary disk models, etc. So this is on GitHub. I put an asterisk a minute ago on it being open source. So currently this is a private repository, but as soon as we release the methods paper sometime towards the end of this calendar year, then it'll all become open and public. And we hope that people really jump in and start using it right away, as soon as possible, basically. So thinking about the future, as I just said, we're working on kind of a methods paper when things will be released. In terms of really expanding this to work for LISA, I think there are kind of two key components to that. The first is just adding in populations that are able to focus on lower masses and higher redshifts, either black hole or galaxy mergers. And then also much more comprehensive modeling of the kind of gas physics. Again, this has already been a large topic of this meeting and other recent meetings. So that needs to be kind of developed more in this infrastructure. And just a quick plug. So one of the ways of improving these kind of source catalogs of mergers, we're developing kind of a new suite of illustrious-like cosmological hydrodynamic simulations that are dedicated to high redshift massive black hole formation and evolution. And I should say that we is different from Nanograv in this case. This is a project led by Laura Blecka at the University of Florida. I and Mark Vogelsberger are also PIs of this. So we're really trying to make a lot of important improvements from the illustrious methods, so improving the black hole seeding models, updating the gas and ISM models, using some cool new numerical techniques like gas hyperrefinement, and improving how we handle the particle dynamics. But again, the details of this are kind of better for another talk. So just to summarize, this new framework holodeck is population synthesis of massive black hole binaries. Right now, it's really being focused for Nanograv, which is supermassive black holes, but it's really designed keeping flexibility in mind and being able to move to LISA in the future. So it rapidly maps from kind of astrophysical parameters to gravitational wave signals. Focus of that is just to be able to do inference on upcoming gravitational wave detections. And the philosophy here is really taking into account the systematics in addition to the statistical uncertainties. So the code release will be soon. It's really designed to be user-friendly, modular, highly extensible. It should be easy to add in your favorite hardening mechanisms, your favorite physical processes. And we're very interested in making sure that that ends up being true. So, if you have some model that's difficult to plug in, just reach out and we'll try to change the framework to make that easier as much as possible. And as I said, it should be relatively easy to extend to LISA. So I think I'll stop there. Thanks so much.
Okay, thank you. Any questions?
So very, very nice talk. I think it's very nice to see the developing this type of tools. I saw that you were emphasizing the binary evolution part, different models that can describe the galaxy merger phase, and also the models for the very small scale gas physics processes like this binary at this stage. But as we heard yesterday, also from the review of the white paper, the main bottleneck for the process binary evolution might actually be at the intermediate scale. You are between few parsecs and a few hundred parsecs. That's where you might actually have stalling or processes like the clamps that we have heard before. You have plans to incorporate that part in the framework. And I think in the LISA astrophysics working group, there's a lot of expertise for that. So that would be an interesting, sub-project within the group.
Yeah, absolutely. So I mean, from the code framework perspective, there's no real difference on the scales. So there's a particular type of class of module for inputting hardening mechanisms, and it's easy to apply that at any different size scale. So those aren't physical effects that we've really been focusing on so far, but it would be really excellent to have those contributed and have those added in. And again, I think that would be fairly straightforward. So if there's anybody listening who's interested, please reach out and we can start working on this right away.
Thanks.
Thank you. Shane, you have a question?
Yeah, actually, Nathan can go because I can walk down the hall and talk to Luke. So,
Okay, that's great. Nate?
Thank you very much, Shane. Hi, Luke. Just very interesting framework. I was just interested. I was just wondering, in terms of the black hole properties there, like on your diagram, you have the masses, eccentricity, redshift, and ... Are the spins in the ... or does this not have spins?
Yeah, that's a great point. So there's kind of a couple of minor hooks in there right now to add in spin evolution. That's something that we've looked at in a separate illustrious-based effort. But so that should be fairly easy to include, but that's not something that people have really been looking at yet. It's much less important for kind of pulsar timing array type signals, so it hasn't been a high priority yet, but should be very doable. And I think that'll also be very important for electromagnetic signature modeling.
Absolutely. Thank you.
Okay, let's thank you again. And then we move to the next one from Section C about those short period massive binding platforms.
Thank you. Can you share my screen? Can everyone see my screen and hear me well?
Yes.
Okay. Let me get rid of the Zoom window. Okay. So hi, everyone. My name is Chengcheng Xin. I'm a graduate student working with Zoltan Heyman at Columbia University. I'm very glad to have this opportunity to present our work. So today I'm going to present a work on estimating the ultra short period massive black hole binaries in LSST as LISA verification binaries. So in case I don't have time to get to my questions or details, I suggest you to check out the paper. I put the archive number on the screen. Okay. So the LSST by Vera Rubin Observatory is planned to launch in the mid-2020s. And when it does, obviously, we're going to enter a new era of time domain astrophysics. Among many of its benefits, one of them is that LSST is expected to discover the largest data sample of quasar yet, so likely in the order of tens to hundreds of millions. And most of these quasars in the LSST catalog would be online by the time LISA launches, most of them. So we all know that quasars are triggered by galaxy mergers, so a significant fraction of these LSST quasars might be powered by inspirally massive black hole binaries, and a tiny fraction of these quasars would eventually evolve into the LISA millihertz frequency band. So we call these verification massive black hole binaries. You can think of these as analogous to the galactic white dwarf binaries, but they're obviously different because they're massive black hole binaries. So in this work, one of the goals is to evaluate the total number of quasars that might be in LSST using quasar luminosity function. So we use a previous work presented by Girish Kulkarni et al. 2019. And the reason we use this work is because they gather a really large compilation of data, quasar data, from almost all major optical surveys. So their quasar luminosity function takes the form of double power law, which is characterized by 4 important parameters. So a normalization parameter, phi star, some breaking magnitude, and also the more important 2, which are the faint and brighten slopes. So all of these 4 parameters are redshift dependent. Kulkarni et al. Used optical survey data to evaluate and bin these 4 parameters at 25 different redshift values. So for our purpose, in order to get a smooth quasar luminosity function, we interpolate the luminosity functions at 50 evenly distributed values of these. So, and last, you can directly relate quasar luminosity to black hole mass under some key assumptions. So the 2 I'll mention is F Eddington is 30%, and we also assume a standard quasar spectrum template. So one last important assumption is that we assume the fraction of quasars associated with massive black hole mergers is approximately 1. So this is one of our first results from the interpolation. We present the estimation of the number of LSST quasars all the way up to redshift of around 7. So our curves are the solid black ones, and we present these numbers for 11 different magnitude bins. So for comparison, we also show the Kulkarni et al. 2019 results, and also the numbers presented in the LSST science book. And you can see that these curves mostly agree, especially in the most relevant range from redshift 2 to 3. And for the brighter magnitudes, for the fainter magnitudes, the curves are more noisy because the data coverage for the fainter magnitude is simply very insufficient. So, and there's also these cutoffs that you see when the magnitude gets fainter and fainter, and that's just from the selection effect from the existing quasar samples. So just to summarize the last page in words, our estimation for the LSST number of LSST quasars down to, for example, a single night LSST exposure is roughly 20 million up to redshift of 7. And if LSST with longer exposure time or co-adding their data sets, they can go down to a detection limit of I magnitude of 26, and that gives us roughly 100 million quasars. So 2 other points I'll mention briefly, but I won't go into details. But these are also very important in my opinion, are that we want to define also is uncertainty in these numbers. And most of the uncertainty comes from the uncertainty in the quasar luminosity function. So we have a section dedicated to this in the paper, if you're interested. And another point that I briefly mentioned already is that the lower LSST detection limit can be achieved by co-adding the light curves with longer term observations. So how do we find the number of compact binaries in the LISA band? So first of all, I'm sure you all seen this LISA signal to noise curve. So I used the one from Robson et al. 2019. I also evaluated the evolution of 3 example massive black hole binaries with primary masses of 10 to the 5 through 10 to the 7 solar mass, assuming a mass ratio of 0.1. So eventually some of these objects would evolve into the LISA band. So I should say in all 3 sets of these curves, I presented 3 redshifts. So Z equals to 1, 3, and 5 from top to bottom. So as you can see in the colored orange area, for example, these could be LSST sources, but they wouldn't eventually evolve into the LISA band. Also for reference, I marked the frequency for orbital period of 1 day when it's right here. So on this curve, one important assumption is I assume a 5-year LISA lifetime. Obviously, this time can be stretched out to 10 or 15 years, depending on how long LISA operates. And this comes from the idea that LSST launches in the mid-2020s and LISA is roughly in the mid-2030s. So that gives the binary 5 to 15 years time to merger to eventually evolve into the LISA band. So given the signal to noise curve of LISA, we use a very simple model to evaluate the number of verification binaries in LISA. So this number is directly scales with a ratio, which is defined by TM. So TM is the time to merger. You can directly think of this as the LISA lifetime, but not quite. But the point is TM is the time that the quasar has at the end of its lifetime to be caught by LISA. And we also assume the quasar lifetime to be 10 to the 7 years on average. So the benefit of this method is that you can directly scale the number of quasars in LSST with this ratio. If you can see my cursor is TM over TQ to obtain the number of verification binaries in LISA. So this number is actually a 3-dimensional number, but for visualization, I present 2 dimensions for now, and then I'll present a third dependence on period in the next 2 slides. So here in the color plot, this shows the number of verification binaries as a function of redshift and also black hole mass, which is directly converted from the magnitudes. So you can see most of these objects are focused on 10 to the 5 solar mass range. And this is consistent with the fact that the quasar luminosity function has a very steep faint end. And also another observation is the sources are also concentrated on redshift of 2. And this is because the normalization parameter in the quasar luminosity function is the highest, around z equals to 2. This set of numbers assumes TM equals to 15 years. So we need to catch the quasars, the LSST quasars in the last 15 years of their lifetime. And the main constraints on how many sources you would get actually depends on how faint LSST can go to. So I quote the number for three LSST detection limits in the table here. For the faintest, which is 26 magnitude, we're able to get roughly 150 sources in LISA. So the third dependence, which I think is the most interesting one, is that most of these binaries that LISA should be able to catch have ultra short periods. So in this histogram plot, I show both the numbers for TM equals to 5 years and TM equals to 15 years. And in the zoomed in plot, you can see even more clearly that the periods of most of these sources are within 1 to 2 day frame. So this is even more interesting in a broader picture perspective, which is you're able to catch these ultra short period massive binary black holes in LISA, and then you might also be able to observe the evolution of these periods, for example, from 1 to 2 days down to a few hours. And this is very robust evidence for the presence of massive black hole binaries, which we're not able to see with the current set of supermassive black hole binary candidates, which typically have periods of years. So we're able to, with LISA combined with LSST, we're able to find these needle in the haystack binaries. So this is my last slide, just to summarize the main point of my talk. First, we evaluate the LSST is expected to discover 20 to 100 million quasars, typically in the range of 10 to the 5 to 10 to the 9 solar mass, but concentrated on the lower mass end, and redshift from 0 to 7. So the second point, which I think is most important takeaway, is that LISA, there might be 10 to 150 ultra compact binaries in future LISA sources. So these are the sources caught by LSST in the last 5 to 15 years of their lifetime. So 2 miscellaneous points that I mentioned are to define the uncertainties of these numbers, we need better faint end slope or even better data for the quasar luminosity function. Again, see details in the paper. LSST might also need to co-add their data in order to achieve the fainter detection limits. and therefore in order to observe the ultra short period binaries. And again, this is important. If we see the chirping of the periods of these binaries, this will be the needle in the haystack problem. And the last bullet points we have, which I have not mentioned previously, is that this analysis can be also done in the reverse direction. So if we didn't have the LSST data before the LISA detection, we can, from the LISA detection, this can also guide the searches of periodicity in the archival LSST data. And this is the end of my talk. Thank you for listening.
Any questions in the audience?
So I know you talk about LSST because it gives you a much larger volume to test. But there are already running surveys where you can at least test the pipeline and see, if, especially if you want to really do this search, like CTF as an example, it does go down to 20.5 magnitude and provides many more epochs what LSST will actually do. So have you thought about already kind of using current facilities, which are plenty out there, to do that kind of, trying at least to set up a pipeline or whatever to do that work, this kind of needle in a haystack work?
Yes, I think that would be definitely an interesting project, but I would have to look into what kind of mass range or redshift range that CTF offers. Yes, that would be definitely an interesting project. There are already existing large data sets, I agree.
Okay.
I don't know.
Oh, you have. Okay. Please go.
You showed the noise curve that you used. Did you put a low frequency cutoff on that, or did you just extract for?
Yeah. So yeah. Yeah, you're asking about the frequency wall. Right?
Yes. Did you put a frequency wall?
Yeah. So I'm not so familiar, but I realized there's at least a frequency wall roughly around 10 to the. Let me see if I can go back to this. This is here. So roughly around 10 to the -5 or 10 to the -4, there's a frequency wall in my understanding. So actually the frequency wall does not have as strong as the effect as say if we were to cut down the magnitude limit, detection limit in LSST. So imposing the frequency limit, for example, would only bring down these numbers by 1 to 2%.
Thank you.
Yeah.
Yeah, sorry, I have one more. It's more like a comment, a warning, which makes the needle and haystack search a bit more complicated, is that some of these sources with 1 or 2 day period, they might actually chirp within an LSST time of a few years. Meaning when you do a period finding and trying to identify these sources with a period, you actually have to add a P dot component, potentially. That's something to keep in mind, which doesn't make it easier, but I think that will be important because you might see the chirp in the LSST event.
Yeah, certainly. I agree. Thank you.
Then let's thank you again for a great talk. And our last talk before the lunch from Giacomo about intermediate math black holes.
Okay, so I'm going to share the screen. Can you hear me?
Yes.
Okay. Sorry. Okay, so hello everybody, thanks for the opportunity to give this talk remotely. So I'm going to talk about intermediate mass black holes. So, and I'm going to show how LISA is unique, is a unique opportunity to find a family of these objects for the first time. So we start with this, this classical picture of the compact objects remnants, and we all know now the existence very well. We have many examples of stellar mass black holes. So essentially the black holes that LIGO has observed, many of them with masses up to about 100 solar masses. We know very well the existence of the supermassive black holes that are at the center of galaxies with masses in excess of about 10 to the 5 solar masses. And so in the middle, in between, we have the population of the so-called intermediate mass black holes. So now we have not had any proof of this object. So like, I would like to convince you like how we are going to very likely find many of them in the next decade with LISA. So, but first of all, why are we interested in intermediate mass black holes? Okay, so there are many reasons. A few of them I have listed here. So first of all, they can constrain stellar evolution. Okay, so because like we know that from stellar evolution, as I will talk about in the next few slides, that we cannot form these black holes as massive as the intermediate mass black holes. So essentially, like finding some of them can put constraints on our understanding of stellar evolution. Then obviously we can extend the scaling relations that we observe for supermassive black holes, like the one that I have here on the top right hand side, where it's the famous M sigma relation. So like this relation has been well established for supermassive black hole. Like the question is, does this extend also to the intermediate mass black hole regime? Then we have accretion. So accretion, we know how the accretion works for stellar mass black holes. We know how accretion works in the center of galaxies when something is accreting in supermassive black holes. And the question is, where is this transition, okay, to which masses? So this happens in the intermediate mass black hole regime. And then obviously, like intermediate mass black holes can be the seeds from which the supermassive ones evolve and form through across cosmic time. And finally, they can influence the environment where they were born and live, and they can be used like in gravitational waves, for example, to test strong or modified theories of gravity. So now just a brief summary about the main families of detection methods for intermediate mass black holes. Okay, so like we have in general 4 big families of detection methods. I will talk briefly about all of them, in particular, obviously, about gravitational waves. So this can be divided into tracking stellar and gas dynamics around the black hole, looking for accretion signatures, looking for transient events like stellar disruption events, and looking for gravitational wave signatures. Okay, so and I will argue that essentially it's gravitational waves the future of the detections for intermediate mass black holes. So let's start with the first one briefly. So we know that whenever we have a massive object at the center of some environment, there is a region called like sphere of influence that essentially tells us the region within which at the lowest order the black hole dominates the dynamics of the objects, okay? And so like you can do this simple calculation. You can see that the most massive INDH, okay, of about 10 to the 5 solar masses, when it's embedded in a typical cluster environment with a velocity dispersion about 10 kilometers per second, there's a sphere of influence of about a few parsecs. Now the question is, the point is that this means that whenever we want to find through stellar dynamics or gas dynamics the presence of an intermediate mass black hole, so we must be able to have to resolve these distances. So like if we put this black hole at about 10 megaparsec, you see that our instrument has to be more sensitive than 0.01 arc seconds. So this is why this is like pretty tough with present day instruments. It's also very tough with upcoming instruments. And so this essentially tells you how, for example, things like what you see on the right-hand side, where there have been like collection of data for the same object, and sometimes this object is being claimed to host a 40,000 solar mass black hole, and a few years later by the same people they said, okay, look, there is not any more intermediate mass black hole there. This tells you that it's very difficult to do this type of measurements, and this can be done only in the very local universe, so basically in our backyard. So what about the accretion signatures? So accretion signatures, essentially, what you have to do is look through your spectral lines of your emission. Okay, you collect the lines, you make sure that your system is consistent not with an H2 emission regions, not with star formation, but it's consistent with an AGN or some emitting black hole. Okay, then what you do is essentially you have proxies that you use in your virial theorem. Okay, as you can see here. But now the problem is that whenever you're doing these things, you are tracking gas dynamics, and gas dynamics does not necessarily obey virial trajectories. Okay, so like there is uncertainty on how you adopt, you exactly use this relation. This relation is defined up to a given constant, and there are many other things that can affect your measurement. Okay, and again, this can be done only for very massive objects and only for the very local ones. So what about tidal disruption events? Tidal disruption events are essentially the case when a star or a white dwarf passes very close to the black hole and it gets tidally disrupted by the tidal force of the black hole. And we have seen many of these events, like tens in the near future, even thousands. We are going to see with the upcoming telescopes of these events for supermassive black holes in underworld galaxies. And we have seen a very nice event like the one that I have here on the left-hand side. Now, how can we use these events to find intermediate mass black holes? We can use them essentially in two ways. Okay, so first of all, looking in the outskirts of the galaxy, as like in this paper back 12 years ago by Lin and Tan, they have done, like looking in the outskirts of the galaxies where you do not have a supermassive black hole. Okay, so like try to see if you find some tidal disruption event there. Or like, for example, looking at the white dwarf tidal disruption events, and the reason for that is that the white dwarf mass to radius relation obeys a different relation with respect to that of stars. And so if you do the math, you will see that the white dwarf disruption event will be luminous only if the black hole is less massive than about 10 to the 5 solar masses. So it means that it's in the NBH regime. Okay, so like if you were to observe these events, they must have been by intermediate mass black hole. So we have a few of these events. The nice thing about the white dwarf disruption events are that they can be sources, so multi-messenger sources, but again, this can be done only within about a gigaparsec or so. So now, what about gravitational waves? Like gravitational waves, we have had this very nice example back to a couple of years ago by LIGO, where for the first time it was observed a black hole merger whose remnant was nominally in the intermediate mass black hole regime. So this very famous GW and DIMO 521 event. So now, if I do a recap of the situation so far, this is our picture about intermediate mass black holes. We have evidence from the first two methods, essentially, that we have circumstantial evidence that we have objects of about 10 to the 5 solar masses. Okay, we have evidence from LIGO Virgo that there is at least one object of about 100 solar masses. And now the question is, where are the intermediate mass black hole of 1,000 solar masses? Okay, so what I think usually people can refer to as textbook IMBHs, like, you know, the 1,000 solar mass. Where are they and how can we find them? So now the question is, the point is, we can find them through gravitational waves. And the reason is the following. So first of all, you can see here in this very, you probably have seen this plot many times now, like about, you know, like the characteristic strain of an event as a function of its frequency. You see on the left, you see here the LISA noise spectral density. You will see here also the ground-based telescope noise. And so you will see that intermediate mass black holes are interesting for a reason. They are the binaries, I would say, like the binaries for which they will start their merger within the LISA lifetime, within the LISA band, and after a few years, they will appear in the ground-based telescope. Indeed, like GW and DIMO 521, the event that I showed you before, if LISA was operating at that time, it would have been probably a source of LISA a few years before it appeared in the LIGO band. And now this immediately tells you that this gives you like a lot of power in constraining a family of intermediate mass black holes by looking at the gravitational wave signatures. But now the point is about intermediate mass black holes. What has always puzzled me about the literature is that there are not very consistent estimates, or like very estimates that are based on like assumptions. Then you work on these assumptions and get your models, like people do for stellar masses or massive black holes. Like for intermediate mass black hole, it's like more, it's a, you know, like a sort of gray area where people do not know exactly what the rates are and like how exactly to make predictions for LISA in a consistent way. So, but you know, like in order to do that, you essentially have two steps. So the first step is you have to form your IMBH. And so we know that from stellar evolution that we cannot form objects more massive than about, say, 60 or 100 solar masses. Okay, and then the second thing is that you have to pair this object to a second black hole and make them merge within the lifetime of the universe. So now for what concerns formation, I always like to show this plot by this seminal result by Rees back in the 70s, where he already had in mind the main ways to form a massive object. Okay, so there are essentially 4 main ways. So the first one is essentially direct collapse from a gas cloud. This has to happen in the very high energy universe because you need essentially like pristine gas. And so this gives you like a black hole of masses like about 10 to the 4, 10 to the 5, so like the very top end of IMDHs. The second case is when you collapse a massive star, like the so-called POP3 stars. This again has to happen at very high redshift because you need pristine gas. And this gives you like typically black holes of about 100 solar masses. So now black holes in between these two extremes can be given through catalyzation through dense stellar clusters. So what happens here is there are 2 things that can happen. The first thing is essentially that stars will first start merging with each other, forming a very big star that eventually will collapse at some point to form an intermediate mass black hole. The second case is instead where the stars first collapse to form stellar mass black holes. These stellar mass black holes inside of the cluster will start to merge with each other, and they form again an intermediate mass black hole. Okay, so like as a good dynamicist, I will talk about the last 2 cases, and I will show you how this can be definitely tested in the next few years or decade with the upcoming ground-based instruments and with LISA. So now let's talk first about the first case, the so-called, what has been called like historically the runaway growth. So the runaway growth is essentially, as I told you, where you have stars that they will first merge with each other and then at some point eventually collapse and form a massive object. Now, what you need to avoid in this case is what people have labeled recently peristability supernovae. Okay, or peristability physics. The reason for that is that whenever you have an object whose core is essentially too big, okay, so if its helium core is too big, this object will either start pulsating, essentially ejecting all the outermost layers, or will essentially blow up completely, leaving no black holes. And so our current understanding of stellar evolution tells us that the maximum mass of a black hole from stellar evolution we can create is about 60 solar masses. But whenever you undergo these repeated stellar mergers, you can definitely see that we can produce more massive black holes, as you can see in these examples that we took from our paper back to a couple of years ago. Now, the second case is, as I said, the case where you start first forming black holes from the collapse of stars. So these black holes in the center of cluster will start merging with each other, producing a more massive object. Now, what you have to avoid here is to be ejected after you receive a recoil kick after every merger, because we know from general relativity that whenever you merge 2 compact objects, so if there is some asymmetry in the merger, these compact objects will receive a recoil kick. Okay, so like this recoil kick, broadly speaking, you can see the details in these very standard and famous papers by Lusto, Hoffman, and Jimenez Fortaleza. You can see that essentially the general trend is that the larger the spins, the larger the kicks, okay? And and also like the smaller the mass ratio, typically the smaller the kick. So what you want is definitely that, throughout your merger process, you will not get big enough kick to be ejected, but you want to be retained in your environment. You can see some example of this in some of the runs that we did in this paper. You will see that what typically happens. Okay, so like you start with emerging black holes, you start having like kick velocities of several hundred kilometers per second, and as time goes on, the mass of the black hole increases and this kick velocity decreases. But so what means it's like it's very critical the first few mergers to be retained within the cluster, but once you are retained in the first few mergers, your object can grow up to a few thousand solar masses. So now, yes.
Thanks.
I did not hear you.
No. Sorry, I was just reminding that you have more or less 2 minutes.
Yes, I'm almost done. So I just want to conclude saying that the thing is that now these type of events are not you cannot easily model them. And the reason is that intermediate mass black holes are in this gray area where you cannot easily model them with typical cluster dynamic techniques like embodied dynamics, and you cannot even model them with cosmological type simulations because they are under resolution. So this is why you need some sort of compromise and develop some kind of semi-analytical methods. And this is what we have been doing in this series of papers, and now where we essentially have a semi-analytical method where we try to include as much physics as possible, including stellar evolution, recipes for dynamics, recipes for recoil kicks, and cosmology. And what you can do is, one of the things that you can do with this kind of approach is essentially you can statistically say what type of intermediate mass ratio spirals you expect. Okay, so intermediate mass ratio spirals are essentially these mergers between something that is at least at 100 times bigger than the companion. So, and we did this, for example, in a recent paper. As you can see, like some of these results where we show the number of mergers expected per year as a function of the mass of the object. Now you can see that this depends on the spin, as I told you, like because every time you have a merger, the recoil kick depends on the spin. This depends on the initial assumption of your seed mass, and so forth and so on. But you can see that now we have like these nice predictions that tells you like essentially how many mergers you expect per year as a function of mass, and you can definitely use the upcoming data from the ground-based or the space-based instruments to constrain your theory. And indeed, what we did, I hope that you can see clearly this in your screen. What we did is actually compute how many of these events will be detected in multi-band. So essentially will be first detected by LISA, and after a few years, they will be detected by the SIGO, eventually this Japanese mission, and by the ground-based instruments like the Einstein telescope and LIGO. So you can see that like our prediction, according to the initial spin that we assume, span from a few events up to a few tens of events per year. And so definitely whatever the result from these missions will be, we will be happy because this will be able to constrain our initial assumptions, and we will keep working on this to make more predictions to constrain our theory. So I will just skip the next few slides since I don't have time. And so I just want to go back to this recap and saying that definitely the question, where are the intermediate mass black holes of 1,000 solar masses, can be definitely answered through looking in gravitational waves, okay? So either in the space-based or the ground-based instruments in the upcoming years or decades when LISA will be launched. And that's it, I will take any questions, thank you.
Any questions? At the moment, we don't have any questions, but as we said many times, please submit them on the website. Okay, then thank you. Let's thank Giacomo again for the great talk.
Thank you.
Now we have lunch.
Yeah, and it works exactly as yesterday. We shut this Zoom and we will meet in a different Zoom room after the lunch break. Thank you to all.